Good morning to everybody. It's a pleasure of mine to announce our first speaker this plenary session this morning. Michel Deza, professor of mathematics from Ecole Normale, Supérieure, Paris. When I asked him what could I mention in order to briefly introduce him as his greatest achievement, he said the greatest achievement is that he is 77 years old now. Yet I would like to mention, in addition, that he has many, many articles and papers on various fields of geometry and related topics. And I just would like to mention from among his 10 books, only one huge encyclopedia of distances. It is an encyclopedia of distances, not only the notion of a distance in geometry and in mathematics, but in sciences and in humanities as well. The title of his lecture is Geometry of the Structure of Viruses. Please, Michel.
So, the virology. Emerging science, so it's in observational stage. So even this such survey which I have here not exist in any book. So purpose of what I will speak that you will have a bird view of what happens on virology in the structure element. But actually some biologists say that biology starts when structure finish. So question of structural viruses is not exactly biology. It is door to biology. So so I will start. Some warming will be about some very small things about polyhedra. For some it would be too trivial, for some too complicated, but very superficial I will say. Polyhedra, polyhedron is just something as a cube. We are in dimension 3. It's convex polyhedra. So we have a point, edge, faces. We can present polyhedra as a body, but also was something which called Schlegel diagram, graph, which vertices correspond to, of graph, black one, to vertices of body and edges. So it is graph, it's planar graph. Okay, so so these graphs called skeleton of polyhedra. So groups. See, it is not important for me to speak much about these groups. There are groups of the body, space group, and the group of the graph. It's not exactly the same. When I speak about symmetry of graph, it's just permutation of vertices which preserve graph. But actually it's about the same. Thank you to Mani theorem. So there are, all these groups are listed. All possible group of polyhedra. What is especially interesting for me, it is what called I icosahedral group or extended hexagonal group, AH. So because viruses main symmetry is icosahedral, this one, we will come to it later. So I said something which is polyhedra. Now mainly I'm interested by this very special, beautiful object which is called fullerene. Fullerene it is just any polyhedron. Fullerene is it is chemical notion. So when I mean here, what I mean here, I mean geometrical fullerene. Okay, it is polyhedron having each vertex have degree 3, and the faces only pentagon exactly 12. And hexagon. Actually, curvature of hexagon, they're flat, they're 0. And the curvature of sphere is obtained just by 12 pentagons, which are have positive curvature. Okay, we not need to much speak about this. So it is a series. All start with dodecahedron. A series which number of fullerene with given number of vertices increase as a great Thorsten, this great guy, prove it indirectly, so, implicitly. We can take from his work, that the number of them increase on 9th degree of n. Okay, so so what I define polyhedron, it in particular Fullerene. Now, this century we even not ask this question, what nature wants. But in 19th century, it was Naturphilosophie. They ask what nature wants. It means it was a hope to find some hidden functionals, which are direct wheel of different things. So what nature optimize? So probably, so what I want to say, that probably nature love Fullerene because Fullerene are the best, in a way, approximation of sphere, and sphere is good. Okay, so I will a little make it more precise. Fullerene happens in capsidovirus. No, I should immediately say what virus have no body. Virus is cell parasite. But virus baby, virion, have body. It's a small piece of protein which it have body, and DNA or RNA distributed on this particle. And when we speak about Fullerene or some others, it is distribution of those guys, those pieces of DNA or RNA, which I will call geometry of virus. So distribution of DNA or RNA on the body of virion. Okay, so a capsid is this particle called capsid. Okay, now, this I have no time to say, but there are some other interesting approach. Now, they appears in chemistry. Buckminster Fuller, the guy who moved it in architecture. But actually, Fullerene appears as an energy minimizer for some interesting problem on sphere. So, probably, so we are very far from real science. It is just the dreams. Probably Fullerene are the best. In nature loves them. Because sometimes it needs polyhedron instead of sphere, and best approximation is probably Fullerene. So, to be more precise, we have a conjecture of grace about volume. Goldberg conjectured something in terms of inscribed. And there are very interesting work of Pisansky and others about other extremely property of Fullerene. So Fullerene are good mathematically, and all this is in stage of a conjecture. But here also conjecture, but which inspires that probably it is this. The reason is here. So very old problem, mathematical. It's going from Steiner. So, but in modern language, it is this. Let's call IQ is a parametric quotient of a polyhedron, but actually it can be defined for any body. Volume, square of the volume, divided by cube of the surface, and normalize it 36p. Inequality, what famous is a parametric inequality, is that IQ is at most 1 with equality if and only if it is sphere. So, maximizing of the parametric quotient is probably nature want. So Goldberg first conjectured for Fullerene. At the time, actually he introduced Fullerene. The word Fullerene was not there, but it is, he introduced them just this way. Now, interesting that independently from all this, in biology, people who study allometric law, how body increase or, I lost my stuff. Okay. Yeah. They actually considered volume divided on sphere. Okay. Okay. Now, so what I said what's polyhedron, what is Fullerene, special interesting case, and make some propaganda very superficially why Fullerene are good as best approximation of sphere. We're still very far from viruses. Now, next step. What fullerene will be especially interesting for me? Icosahedral one with highest possible symmetry. So, I cannot control it at all. Okay, it happens that all of them have particular number of vertices, 20 times. So all of them are parameterized by one complex number, actually one Gaussian, Eisenstein, Eisenstein number. But we don't need all this. By two integers. This way. I think I will just say how this parameterization go very quickly. Oh, okay. Sorry, I should find my transparence where it is. Okay, I couldn't find it. Yeah, okay, here. Oof. So, no, sorry, I just went not very well. Okay. So, icosahedral fullerene. They are parameterized, I will say later why and how. Smallest icosahedral fullerene is dodecahedron itself. Next one is truncated dodecahedron on 60 vertices. This guy, it is truncated dodecahedron, and this is what called chamfered dodecahedron. If you take dodecahedron and chamfer it each on edges, each edge became a hexagon. And other one is the first fullerene which have a icosahedral symmetry but not extended, just 60 elements. It is 440 elements. So there are icosahedral fullerenes. Now, what happens in viruses? Dual icosahedral fullerene. Dual icosahedral fullerene, they have 12 vertices of degree 5 and all other vertices of degree 6. And it is all faces are triangles. So they appear as geodesic domes of Fuller, as capsid of viruses, and in carbon. But sometimes structure of virus is actually not dual fullerene, but fullerene itself, but rarely. Essentially, when we have icosahedral virus, it is icosahedral, but everything could happen. Okay. Each icosahedral fullerene could be parameterized by two numbers. First, I just will say very superficially how we can see it. Let's take what some icosahedral. It has 12 vertices of degree 5. So take two neighboring ones, this one, and say, this one, and say this one. How we can reach here? 1, 1. So in one direction we make a 2-step. In other direction we make 0-step. So it's 2, 0. Here from 5. Where is 5? 1. And here is this second one. So 1, 1, and 1 step in this direction. So it's 2, 1. So it is just superficial way how parameterization go. But actually it goes this way. Each icosahedron can be obtained this way. You take an icosahedron and you throw it on the triangular lattice. I don't know what happens with my slide. So you throw it somehow. What means it should you throw so that triangle became lattice polygon. It means each vertex will go in lattice point. And then you will get, I don't know what to do, then you will get two numbers. I will try. Okay, you can catch it here. We get two numbers, 1 and 1. It will be the parameter which characterize icosahedral. Icosahedral you will obtain the following way. You have this, after add other one. So all triangle will be completed. And then take a dual graph. when you put all 12 faces of icosahedron on the plane, you will take a dual graph by the following way. Each six valent vertex became hexagon, and 12 vertex of original icosahedron became pentagons. And this will be construction. And then take a dual, you will get icosahedron. So all icosahedral Fullerene come by this Goldberg-Coxeter operation. Okay, here are some examples. The first example is herpes. Actually, virion of herpes under cryo microscope, it is actually doing this. Having this form. Some other viruses. So, Icosahedra, example of Icosahedra appearing in architecture, famous examples are here. So what means it here, for example, this is dual truncated icosahedron. So all of them with full symmetry. All these come from Buckminster Fuller, but I will not have no time to speak about him. Some of geodesic domes. Now we come to viruses. Now about 15 minutes I will speak only on biology. Okay. Life. What's life? As now, life is cells, cellular life. Okay. Viruses, let's call them, because what is cells? Cells have a protein and DNA. Actually double-stranded. Now, half-life, cells parasite. They have a, in adult stage, if they succeeded as virus, they have only DNA RNA, by which they implanted original DNA of a cell, and they have no body. Cell parasites. No, satellite is just special kind of viruses. Okay, now there are something even less, there are some pieces of life even smaller. And there are even smaller than smaller prion, which is total mystery. It is just protein without any DNA. Just a crazy protein. Basically, mystery. Because perhaps there are some small pieces, which is prion. Now, what viruses? Viruses originally, infected cell release virions. And all of them die, majority. Very rarely they succeed to become actually virus, to come to cell. So they can be very, oh, боже мой. Okay. Okay. I just not control it well. So diameter from 18 nanometers till 3,000 nanometers. Much more virosphere by biomass, much more than all eukaryotes, so including all us, of course. So about 10 viruses exist for each cell. Phages, it is a name of viruses which specialize only on bacteria. Every day they kill about a third of all bacteria in the world. And so global population is estimated as 10 to the 32 degree. What? Okay, I will go more. Oh, it is example of virus. Some viruses are very big, giant viruses. Mimivirus, it's called mimivirus. It is interesting because it's first virus for which was found its parasite, not satellite. Satellite is the virus replication of which depends on some first virus, but it's not an enemy. This is virus have virophage, some smaller virus which is a parasite. What's interesting that largest viruses are bigger than the smallest bacteria, because some bacteria are endoparasite of other bacteria inside. So large viruses could be bigger than the smallest bacterium. Oh. Okay, virus evolution. Okay, so beautiful thing that there are something. Okay, what to do it? Okay, there are something as a viral sex, which analog of sex for viruses there are. Okay, impact of viruses. Viruses, after many generations, they start to be less negative. And finally, they finish in genome of host. So in long term, it's not clear how it will finish. It's perhaps even in long-term collaboration. So nobody knows what is this big open question. How its coevolution go? Okay. Sorry. Oh, I don't understand what to do. How to make it? Oh, yeah. Yeah. Interesting about cancer. There are some viruses which initiate cancer, oncoviruses. But also there are some viruses which are oncolytic, which kill only cancer cells. Because of that, some studies, especially in China, they try to build viruses which kill cancer cells. It's very, very dangerous because we don't know what will happen. So it's a big open question if this research should be done or not. But some people work on it. Okay, what to do? So the war, to make war to virus, actually, as now, only 10, or actually 8 virus species are wiped out. And only one disease was eradicated by vaccine. It's swallowpox, because it started a century ago. Now, they basically make love. So it's clear that that sex appears because cells have no other way to defend themselves against viruses, because mutations, it's something which is difficult for virus to jump. So origin of sex is defense against viruses. So so about 40% of our genome, it is come from viruses. So our genome is full of junk, which not logic actually, because we are survivors of very long evolution. So many junk. And about 40% is proved that it was genes from viruses. Something was useful, something not. So as now, the idea of trees that will come by some vertical evolution by trees is destroyed into and horizontal gene transfer probably was decisive for evolution. So, origin of viruses, it's unknown. There are 3 theories. There are arguments for each of them. One, virus first. That the capsid, that in beginning there was even not parasite, that it was first entity. And then they come before last universal cellular ancestor. Then 2 theories speaking about hoping that cell was the first. One of them, theory Vagrancy, explain that small viruses come from pieces of cell, from transferable pieces of cell. And degeneracy theory says that big, as mimi virus, giant virus, come by reductive evolution. Because sometimes evolution go over simplicity. It's not always going over complexity. Okay. Okay. No, all major transition could be explained by action of viruses. So the big picture. Viruses are dominant, most abundant, diverse Earth ethnicity. Viruses probably their idea to call them acetota, to introduce fourth domain of life. Eukaryote, archaea, and bacterium, and acetota. We don't know. Come back to mathematics. Yeah, symmetry of viruses. Capsid of virion. When we speak about symmetry of virus, we can speak in two ways. One, if it is about baby virus, virion. Second way, it is about envelope. Because some viruses, when they enter in cell, they force cell to create envelope to protect them. And this is cell do. This envelope also have symmetry. Okay, so how to check virus structure? Viruses happens on the boundary of our capacity to see. So for many viruses, we cannot, electron microscope not work cryo microscope. What they do? They kill virus. And virus became dead body, and they consider diffraction of this body. And this is beautiful picture which I will show you. It is a picture of the come from diffraction pattern of a dead virus. So it's not exactly structure, but it's what we can get. So actually, as now we know that there are many symmetries. Icosahedral just more interesting, more studied because it's close to many our sicknesses. But at large, there are following symmetry. Icosahedral, capsid. Now, icosahedral with envelope. Helical, and some, everything, even brick. There are some form of brick. So, helical. So, there are some small mathematics here. Okay. So, we can describe, of course, mathematically. Complex structure could be this. So there are some outlier. Now, how it started? Crick and Watson, already having a Nobel Prize, in 56, they already DNA was found as double spiral. They say that small viruses are either rod or spheres. Actually, they expected that will be form of Platonic polyhedra. Okay, but what happens that what we know what we see? All virion are helical or icosahedral. It's what we have now. There are some non-icosahedral form. I will speak also. There are icosahedral fullerene type. There are icosahedral which are not fullerene type. And there are some mysterious with weaker icosahedrality. It's very, it's very messy. There are no good, nice theory. So icosahedral viruses. Protomer. When we have a capsid, this small body of virion, actually the DNA is not a point. It is a ring. It is a ring. Some ring of 5 protomers, some are ring of 6. We cannot work with them as rings because it's too small. So we consider them as a 5 or 6 valent capsomers. So it's rings. So which are connected by protein interaction bonds. So the bonds, bonds are flexible, very, very small. So those guys, Gaspar and Klug, got a Nobel Prize for the following observation, for the following human idea, not proved, just conjecture. Virion minimize free energy by organizing copsomer quasi-equivalently, actually in icosahedral. So they explained only one particular case, but most popular in time. What means quasi? No, I will explain it later, but in 2 words it means the following, that we have a local symmetry, icosahedral symmetry, but it's local. Now, the whole things will be explained when we can evaluate capsid free energy by all atom simulation. But modern computer cannot do it. So all this, because we cannot make a full computation. So again, this Goldberg, etc. construction to explain. Now, capsid, this icosahedral capsid, have I think I have no time to explain it in detail. Okay, I will just explain for what they get a Nobel Prize. That copsomers, vertices of this icosahedral are similar when they stay on the same triangular face of original icosahedron. You remember that icosahedron come from icosahedron thrown on the lattice. So if they stay, vertices stay on the same face, they are similar, but not equivalent. And there are this T, this is T is triangulation number, number of different non-equivalent positions. So what we have? We have something less than equivalent, something which approximates probably free energy. Okay. I was not very clear here, but okay. Now, here are some funny things that many thousand years ago, Hippocrates said that all diseases come from icosahedra because icosahedra is water, or it's too much water in organism. Actually, he was right. So, now some icosahedral viruses. Look how this looks similar to the architecture things, you know. So exactly as geodesic domes, many viruses are here. And there are, for example, very beautiful situations which still very difficult to explain. For example, some viruses, you know, when you have a chiral, if symmetry is full symmetry, we cannot have chirality. But if we have just 60 elements, it could be levo or dextro. And some virus just differs by chirality. How it's connected biologically, it's open question. So it's still unclear. Now, some examples. Actually, this is a moment to say how the virology come out. The first virus was found by Russian guy Ivanovsky. Yes. And first seen was only 31. So theory of viruses is just in beginning. Now, the example of what happens is pseudo-equivalence. Because as now, when I spoke about protein, I consider protein is same for everything. But actually, protein could be different. And protein being different, we can put it by different colors. And then we have a reduced equivalence. Equivalence which preserve for not quality of protein. But it's just small piece of biology. But many actual work is here on this pseudo-equivalence. Now, after many observations, I will just show beautiful virions. Again, herpes virus. Yeah. Now, first, it was one big problem that some case we had an icosahedral symmetry, but it not come from it not come from icosahedral. It was a big problem. It's called, and there are some German, now she's not so young, Tvarok, who actually solved it by following things. Actually, icosahedrality is not necessarily could come from polarion. It can come from quasi-crystal structure. So I will not explain how she get it, but basically she constructed Penrose pattern, a special case of quasi-crystal, and this explained mystery. So it's a very good girl, Tvarok. Okay, so it's now. So I will speak a little about quasi-crystal. So in dimension 3, lattice cannot have icosahedral symmetry because axis cannot be of degree 5, axis symmetry. But what is quasi-crystal? It can be defined by local rules from down up, but I prefer from up to down. It is basically what? We go in dimension 6. Then we have a lattice, which have a icosahedral symmetry. After projected on dimension 3, what we obtain is not a lattice, it's something which inherited some nicety from dimension 6 and keep icosahedral symmetry. It is quasi-crystal. As simple as this. So here it's mathematics, but we will skip it. Mathematics, I will skip. So what happens now, what we can call kind of theory in virus structure? There are no unit theories. There are several talented persons who did some partial things. Now, first, very nice observation of a region Tvarok. She got icosahedral tiling by projection from D6, which described some mysterious real-life viruses. Now, there are American way, what this here. Computation, heavy computation, expensive. It's worked very well. They computed something, and they got for small value everything which was done before. Still, no explanation. Just extremal objects, what they found, included all extremal objects explained by this. Me, I prefer with this what Alois Janner, Dutch crystallographer, who write absolutely unreadable paper, which I spent time to read, and it was main work for me. What he did in 2 words, He presented as candidates for icosahedral viruses the following. Take icosahedron, just icosahedron, 12 vertices, 20 faces. Take 6 diagonals going. Now, on each diagonal, take some point from the center. Take any, just 1 millimeter or 2 millimeter. You will get 6 different vectors going on diagonals. So, but it's going in both directions, so it will be 12. And now take all linear combination of those vectors with integer coefficient. He says that this will be icosahedral object which cover all viruses. And it looks that he's right. So it's cover all known things. Still, it's too large. So I like this theory because mathematically so simple. Now, all this, what people study now, it is virus in one position. But viruses, dynamic of viruses if needed. There are several papers when people try to attack virus dynamics. And then it was some representation theory. So, of course, I will not speak about it. It is just beginning, but they try to do something. They explain some small things. Oh, I forget to say important things. General conjecture of Janner. Capsid acts as a resonator with nodes of wave-like Asian modes in various points of icosahedral lattice. It is his general conjecture. We don't know. Okay. So now, viruses, just examples. So some viruses force cell produces spike, not only envelope. So then we can speak about symmetry of spike. So there are different ways to speak about structures. Also, I want to say, answer the question, knowing structure of virus, is it useful or not? As now, almost not. Except only one situation. When virion approaches cell, you have problem of entering in. It puts some things, some epitope, some chassis, let's say, as a plane. So this related to structure of virus. So in this way, when we know structure of viruses, it could help. Otherwise, it is just hope that it will be useful. So in big books of virology, there are listing of different viruses, and in the beginning always there is something which they call triangulation number. If virus icosahedral, they give this a square plus b square plus ab, where a and b is pair of integers which parameterize some icosahedral diagram. So this number always given when it's possible. Especially because majority of our sicknesses coming from viruses are icosahedral, as Hippocrates already said. Now, how far it can go? It can go very far. For example, mimivirus, largest known, he have triangulation number in this area. No, actually, majority of viruses is not for us. Majority of viruses is for bacterium and for plants. And they are not behave exactly as our. So our piece of virology is not typical. We are very small in the listing of living things. Other shapes. It's my last 5 minutes. AHV. AHV, actually, we cannot see. It's strange, we cannot see exactly what happens. But it's conjectured capsid of AHV. Will be not dual fullerene, it will be fullerene. Moreover, conic fullerene. It means we have 12 pentagons distributed this way. 7 pentagons on one side, 5 on other side, and all other are hexagons. It is conjectured form of AHV virus. And also, there icosahedral structure of spike which it produces, because this virus is enveloped. So this virus force cell to. This is possible structure of virion baby. But this once babies enter in, it gave up his body, but forced cell to produce envelope. And envelope have spikes. So it is also icosahedral. Conic fullerene, but it's not still known more than this. There are some variation. For example, there is something which was observed, some fullerene coffin. They call fullerene coffin such a fullerene in which 6 pentagons here, 6 pentagons here, but they organize it in the following way. 5 of them form a circle, and around one. There are 1 pentagon and 5 pentagon around him. Here we have a 6 pentagon forming circle. So this was observed on some strange viruses, and they call it fullerene coffin. So now very complicated these avian viruses, pox viruses. Now, it's my last guy. I was too quick. It is the most complex known virus. It is phage T4, who have following form. Oh, I speak about virion. Virion have a body, have a head, which is icosahedron, and long tail, helical one. So there are many people who study geometry of this guy. So there are some mathematics. I also try to study this body. So there are some geometric observation. So there are study of elasticity for viruses, but again, I have no time to speak more in details. That's all.
Thank you very much. Thank you very much for this inspiring lecture. Questions and remarks?
Yeah.
Thank you for your lecture. Why Fullerene goes easily inside cell?
In 5?
Inside cell.
I'm not good.
Fullerene легко проходит в клетку.
No. We don't know how. I not say that Fullerene going in cell. No, it happens that some viruses, baby, have a form of a dual Fullerene or Fullerene. Now, how they go inside of cell, it is absolutely irrelevant question. We just hope that by knowing structure, we can predict where virion will put epitopes, chassis. Because this small baby Fullerene, not Fullerene, but this small virion who have probably form of Fullerene, if we consider the DNA as a point of a polytope, then we can speak about Fullerene sometimes. So once we know structure, some study can deduce from it where this virus produce epitope. So we can can fight it. That's all. But Fullerene not help at all. Fullerene just one of the possible structure, majority for our human sicknesses, not majority for all viruses.
Thank you for your interesting talk and presentation. You have been discussing the outer form of the capsids, and you mentioned on one of your slides chirality, left and right
Yeah.
forms
Yeah.
logically. But viruses can also crystallize, and it's known that when they go to the classic 32 crystallographic groups,
Yes.
especially in the lower symmetry groups.
Yes.
And in certain cases, they go to the enantiomorphic, or what crystallographers say enantiomorphic.
Yeah, different chirality, yeah.
Left. And maybe you know that this is maybe the most important thing which even academician Vernadsky in the beginning of the century was speaking, the distinguish life forms from not life forms, from minerals, etc. So I think that the problem with the virus is, in what's your opinion on the enantiomorphism? Because in life forms we have only one form, enantiomorphic.
In life forms?
Like DNA, for example.
No, but yeah, I understand.
Spiral, you say.
Yeah, I understand.
And in viruses we see that we
Two, both.
Maybe here is the enigma of transition from life form to...
I think we just have no data enough to. No, okay, what you say is big dream. When at stage much lower stage. So in the structure of viruses, first of all, not all viruses are icosahedral. Not all icosahedral viruses. But some of icosahedral viruses which have not complete icosahedral symmetry, then they can speak about levo and dextro. So yes, it exists both. Both exist in the same way. Some people think that dextra will go on the south of Earth, But it was in beginning such study, but after it was contradicted. We cannot explain why Dextra one level. There are studies which try to explain that extra level and extra connected, for example, to human, rabbit, because there are pairs. Virus acting on the south hemisphere, same virus acting on the north, and they differ by chirality. So big dream that it is related to acts of magnetism and everything. So many conjectures this way was disproved actually by. So there are actually many dead conjectures in this area. So chirality in virus structure are not explained as now. But both structure appears on viruses. It's mystery.
It is known that in certain chemical compounds, the left-handed version is completely harmless, but the right-handed version is harmful. Can happen the same phenomenon for viruses?
Yes. Because first of all, not many cases which you completely studied. I think it's about 15 to 12 cases when just two viruses differ by, because it's very rarely when we have it. So virus can actually, in general, to go in sleeping mode and stay sleeping. AHV, for example, how it's do. Sometimes it survives by just going sleeping. Several years later, it's wake up. So it is deeply observational stage in virology. Pretension of the science exists. When I went in this, I found all what remains of science I actually collected here, which remains science. It is observational stage. Yeah.
Is it true that in terms of this triangular equality, chirality means that none of A and B is 0 or they are not equal?
Yes, of course, you're right. Yeah, totally right. So the B is between 0 and A. And chirality exactly happens if and only if B is not equal 0, B not equal A. Moreover, these parameters define geometrical structure uniquely in the case when it's full group. And non-unicity is possible only in chiral case. So for large A and B.
I'm very sure that the knowledge about the symmetries which are in viruses can have a big impact for the designing of new medicines against.
Of course.
But it is not yet so developed.
No, there are. There are many good. As in general in medicine, many things work, but we don't know why. Medicine make many. So of course people work as crazy because viruses are actually. But now, what a slide which I not explain, there are computation. How we die? We basically die from infection from bacterium. As now, bacterium take about 40% of death, and direct death from viruses is about 30%. So main fight is against bacterium, because bacterium kill us more. So more knowledge about viruses, less knowledge because they're more complicated. Yeah.
Nowadays, the fundamental feature of all the diseases humankind has is inflammation. Inflammation is, of course, connected by bacteria, but it is
Result,
a common feature of all the.
Yeah, I agree. I completely agree. Yes. No, but it is already, we described stage of sickness, yes. But I spoke about agents. In terms of agents, bacterium is now, actually we have even some sicknesses coming from archaea, from eukaryote. But basically bacterium kill us. Unfriendly kingdom.
I think so. The further is one more question.
You're completely right. It is only one way to see how get a free energy, because clear that that particle of virion should minimize free energy. It's poor guy, he have very small piece of protein. How to distribute, make economy, so minimize free energy. But as I said, to compute free energy atom by atom, computer cannot take it. So it's why Kaspar Klug got a Nobel Prize for approximative idea for some class of viruses. But moreover, once this computation be done, model should become dynamic, because real things is dynamic, because virus is changing every moment. So even things which static is not done. But computer, one going to this, so probably in 10 years, computation will be done for static model. A dynamic model will wait.
I think so. The discussion
Yeah.
should continue in the break. Thank you very much.
Thank
again.
you.
We have half an hour.
Thank you very much.
As usual,